discuss alternative ways of calculating concentrations. We discussed molarity previously, and that's the standard there, and that's why we discussed it so much. And it's just the moles of solute divided by the liters of solution. We like it because it contains moles in it, and so we can use that directly in stoichiometric calculations, and we can find the concentration of different things just by using an equation. So molarity is the standard in chemical calculations typically. Another one that's an alternative to molarity is known as molality, and it's lowercase m. And molality is defined as moles of solute, same as up here, but now it's divided by the kilograms of the solvent, not the liters of solution, it's the kilograms of solvent. Okay, so it's a little bit different. All right. And we use that in other calculations. You'll see that later on after these examples. This we've discussed before, mass percent. It's just the mass of a component in solution divided by the mass of the entire solution. It's standard beyond chemistry. It's how we calculate mass percent of anything. Whenever you have a mixture of anything, it's the mass of one thing divided by the mass of the entire thing. And for percent, you multiply by 100. And we use that because, using things out of percents makes sense to us. We can kind of visualize things out of 100. But a lot of times, the mass percent ends up being very small. So imagine you calculate your mass percent and it ends up being like 0.0005392 or something like that. That's kind of annoying to write all these zeros. So we've devised an alternative to mass percent, and that's parts per million. And it is the same fraction as this. You see that? Mass of A divided by mass of the entire solution. But instead of multiplying by 100, I'm multiplying by 1,000,000. Okay? And another alternative is parts per billion. And again, it's the same fraction, but you multiply by 1,000,000,000. Why do we do that? Because sometimes in things like, for example, environmental applications, the EPA would set a standard for a pollutant in water, and the pollutant concentration will be very, very low. Why? Because even in very, very low concentrations, it could cause harm to organisms and to humans. And the amount that is needed just to be deleterious is so small that it would be silly to express in mass percent, and we express them in parts per billion. So it will be something like, say, 50 parts per billion or something like that, which if you wrote that in percent, it would be a lot of zeros before you hit the 5. So we just use 50 parts per billion because it's more convenient. They're equivalent. You can see they're identical. You just multiply them by a different number to express something. Okay? Just note the thing that I'm multiplying by is known as the mass fraction. Okay? And for 3 through 5, make sure that when you apply these equations, they all have to have the same units. Otherwise, it doesn't work. So let's do some examples. Hopefully, that will cement the ideas better. Let's go over molarity. Again, we've seen it before, so I'm not going to dwell too much on it. I'll do one example to remind you of molarity. So calculate the molarity of a solution. Let's say a solution contains 1,000 milliliters, and in it we have, say, 25 grams of NaCl dissolved. Okay, and I want to know the concentration in molarity of NaCl in this water solution, in this water aqueous solution. So what I would do is, again, I would try to apply the definition of molarity, and molarity is moles of solute divided by the liters of the solution. Okay, and I see here the moles of solute. I have to identify which one is the solute. Well, NaCl is a solute, and water would be the solvent. Okay, we typically would have water as our solvent. So, since NaCl is solute, I have to convert 25 grams of NaCl to moles of NaCl. Okay, so that's fairly simple. I'll just apply the molecular weight of NaCl, and I get 0.431 moles of NaCl. Okay, cool. So now I got the numerator, check. The denominator, I need in liters, I got that in milliliters. Well, that's simple, I can just convert milliliters to liters. And I chose this on purpose just to make it easy. 1,000 milliliters in 1 liter, so obviously it's 1 liter solution. And finally, molarity is equal to 0.431 mole of NaCl divided by 1 liter solution. And the answer is 0.431 molar. Okay, fairly simple, fairly basic. Just a rehash of what we had done before. Now let's look at molality. Something has molality, which would be lowercase m instead of uppercase m. And let me give you an example here. Calculate the molality, kind of hard to say, especially when you have a dry mouth. Molality of a solution containing 5.05 grams of C10H8 dissolved in, so I chose this on purpose because it's not water, dissolved in 75.0 milliliters of benzene. Okay, perfect. So now I have to identify solute and solvent. So this guy here is going to be my solute, and then this thing is going to be my solvent. It's dissolved in it, so it's my solvent. Okay. Now, my expression for molality is moles of solute divided by kilograms of solvent. Okay? Right. Oh, one more thing I forgot to give you in the problem statement, the density of benzene. That's important because how would you do that otherwise? Density for benzene, D of B, is 0.879 grams per milliliter. Okay, so I need moles of solute and kilograms of solvent. So let's do it in two pieces. The moles of solute, I got for solute, I have 5.05 grams of solute, and I need to convert this to moles. Simple. I just do the regular thing. So this thing, if you calculate the molecular weight, is 128 grams per mole. Okay, and this ends up being 0.0394 moles of solute. Okay, let me just rewrite that because it's a little hard to see. It's 394. Okay, now I need my kilograms of solvent. Well, what do I have for solvent? I have that it's 75 milliliters. How the heck would I get to kilograms of solvent? Well, let's just do some dimensional analysis as we've been doing. So I need to go from milliliters to kilograms if I can. Well, I give you the density of benzene here in milliliters and grams. Cool, so I can convert from milliliters to grams, and then I can go from grams to kilograms quite easily. So I'm going to get rid of milliliters and go to grams using density. And then I'm going to get rid of grams and go to kilograms using the fact that I know that 1,000 grams is a kilogram. Okay, and then I should get my kilograms of benzene. So using the density here, the 879 goes with the grams, and it's 1 milliliter. And when you punch it all in, you should get 0.0659 kilograms of benzene. Okay. Lastly now, I have my moles of solute, I have my kilograms of solvent, and I can calculate molality. Again, it's the mole of solute divided by the kilogram of solvent. So I get 0.0394 moles of solute divided by kilograms of solvent. Okay, and then once I punch that into the calculator, I get that this is 0.598 little m for molality, C10H8 in benzene. And that's how I would calculate molality. Very similar in mechanics to molarity. Now, having done that, let's go out of molality and molarity, but they're very similar, and go into the realm of concentrations using mass percent and parts per million and parts per billion and things like that. Okay. So, calculate the concentration So I picked something that's hopefully fairly simple to use. Calculate the concentration in mass percent, parts per million, and parts per billion when I have 25 grams of salt dissolved in 100 grams of solution. Okay. For all of them, what we need is the mass fraction. We need mass of NaCl divided by the mass of the solution. Okay, and then you multiply it by 100% to get to mass percent. You multiply it by 1,000,000 to get to parts per million, and you multiply it by 1,000,000,000 to get to parts per billion. Okay, so I have that. Let's do it. I give you the masses directly. I chose it on purpose, so just for illustration. 25 grams of NaCl divided by 100 grams of solution. So let's do it 3 times. Times 100, times 1,000,000, times 1,000,000,000. So 25 divided by 100, that's 0.25. 0.25 times 100, that's 25% NaCl in water, or in solution. Times 1,000,000, I have that. Ends up being 250,000 parts per million. Okay, and times, I miswrote this is 10 to the 9th, times 1,000,000,000, I get 250 million. So not very convenient to use parts per million and parts per billion for this example, because they're so big. Sometimes you have this is so small that these become really big. Okay, so that was just for illustration. Let's do an example that's a little bit less straightforward. So let's continue now. And let's find the concentration in parts per million for a nitrate solution in water. And it is 45 milligrams per liter NO3 minus in solution. And take the density of the solution to be 1. Okay. So what I have here is 45 milligrams of NO3 minus divided by liters of solution. And I'm trying to get to parts per million. So what I need is something that's milligrams of, say, NO3 minus divided by the milligrams of solution, and then times 1,000,000, and that will give me parts per million. Right, because I need them to be the same units, the top and the bottom, and they have to be in terms of mass. So if you look here, I just got to convert the denominator to milligrams of solution. Alright, so let's do that. And I give you the density of the solution, so you can convert from volume to mass. So I give you liters, but the density is in milliliters. So let's convert liters to milliliters first. So to get rid of liters, 1 liter of solution is 1,000 milliliters of solution. Cool. Now I have milliliters. I don't want milliliters. I want the kilograms eventually. Milligrams eventually. So I'm going to convert to grams first because I'm given the density here in grams per milliliter. I'm going to cancel out milliliters, so I'll put the milliliters at the top. 1 milliliter is 1 gram. That's the density. Okay, now I have grams at the bottom, right? I cancel out the liters. I cancel out the milliliters. I have grams at the bottom. I want milligrams to make sure they're the same. And I know that 1,000 grams, 1 gram is 1,000 milligrams. And that will give me milligrams per milligrams. And to get to parts per million, so now I have milligram per milligram, I multiply by 10 to the 6th. So now you punch everything through the calculator and you should get your answer, and your answer is 45 parts per million. Okay? Let's express this in mass percent. So to do that, it's the same thing as here, but instead of multiplying by 10 to the 6th up here, I'm going to multiply this by 100%. Okay? And when I do that, I get 0.0045%. So you can see this is not as convenient to write as 45. So that's why we came up with this. Okay. And that's really like the crux of it. And express in parts per billion, well, it's exactly the same thing as here, but instead of multiplying by 100, I'm multiplying by 1 billion, and I get 45,000 parts per billion. These are all identical. They're equal to each other, but we choose this because it's more convenient to work with, because it's a number that's small enough to work with. That's the only reason we're doing that. So I suggest doing a whole lot of examples yourselves, a lot of exercises here, because there's a lot. This could get pretty tedious with the different types of calculations.